Hi all. The aim of today's lecture is to use the transportation method, which we've covered in the past two lectures, to try to prove concentration inequalities for functions that don't just have the standard bounded differences property for which McDermott's inequality applies, but the aim is to actually relax bounded differences conditions as much as possible. And in today's lecture, we will actually see a very powerful example of such a condition for which the transportation method can readily give us answers. So before we start, let's just take a few moments to review what we have seen about the transportation method. Now the core ingredient, as you recall, of the transportation method or transportation cost or optimal transportation method for proving tail concentration inequalities is what is called the transportation lemma, which is essentially a bridge between uh, control of the moment generating function or the log moment generating function and control of differences of expectations of the quantity that we want to control with respect to different probability measures. So the transportation lemma basically says, one version of the transportation lemma says that you can enjoy sub-Gaussian moment generating log moment generating functions if and only if you can show that certain transportation cost type terms like EQZ minus EPZ for two different probability measures Q and P can be bounded, let's say, as square root of the KL divergence between them. So these two statements are equivalent. And in the last lecture, we were able to prove the famous McDiarmid's inequality or bounded differences inequality using this very recipe, which is given by the transportation lemma. So in the course of doing that, we essentially reduce the problem of showing McDiarmid's inequality for a bounded differences function f or z equal to f of x by by reducing to the problem of exhibiting a coupling between a product measure, which is the distribution of the x's on which the function f is applied, and the other measure to be coupled is an arbitrary measure q over n symbols, let's call them y1 through n, such that the following inequality held, which is that the summation of the squares of the discrepancies at each coordinate should be bounded by the KL divergence, okay, the overall KL divergence between the n-fold probability measures. And this is basically like an optimal transportation cost inequality, which is called Martin's transportation cost, which Martin's transportation cost lemma actually shows. So this is exactly the content of Martin's transportation cost lemma that we proved earlier. The ingredients in showing this result were basically Pinsker's inequality that helped us deal with the n equal to 1 case. So in n equal to 1 case, it says that the probability of x1 not equal to y1 should be at most the square root of half the KL divergence between x and y, between the distributions of x and y. And this is exactly the famous Pinsker's inequality, which was proved using the notion of a maximal coupling. Okay, and to extend it from n equal to 1 to general n, we used an induction argument at the heart of which was the chain rule for KL divergence. So just to remind you of what this chain rule looks like, it basically says that the divergence between Q on n symbols and the product measure P on n symbols, or in fact any measure P on n symbols, is equal to the sum over all I of the conditional KL divergence of yi given y all the way from 1 to I minus 1 with respect to the P measure for the conditional P measure for xi given all symbols x from 1 to I minus 1. Recall that the notation x subscript something superscript something denotes the vector consisting of x starting from the lower index and all the way moving up to the upper index, and when convenient we will omit the 1 in the subscript as a default. Okay, so this is conditioned on the realization q a realization of yi minus 1 and averaged out with respect to the q measure of y1 through I minus 1. Okay, so just to make it a little more precise, this term is just the conditional KL divergence is just defined as expected value of a vector of I minus 1 symbols distributed according to q, the marginal of q on the first I minus 1 symbols. So once you have fixed y, small y1 to I minus 1, you just go ahead and evaluate the standard KL divergence of the conditional measures yi minus 1 equal to small I y minus 1 with respect to the same thing done for p yi given yi minus 1 equal to small y I minus 1. So this is the expression for the chain rule for KL divergence, and we saw that you could essentially extend a coupling for n minus 1 symbols xy up to length n minus 1 using uh, coupling ideas to a new coupling which covers an extra symbol, so xn coupling to yn. Okay, so that was basically a recap of what we did with the transportation method in order to prove the bounded differences inequality or McDiarmid's inequality. Now let's try to move beyond this and try to see how much flexibility the transportation method allows us to deal with functions that are not strictly uh, having bounded difference properties. So let's call this beyond bounded differences. Okay, which in other words is also McDiarmid's inequality using transportation, using ideas from transportation. Now let's consider a setting as follows. Consider a function f which is not which satisfies a property that is weaker than the bounded differences property. So f is a function such that, let's say, f of x minus f of y can be bounded by an x dependent type bounded difference vector of the form ci of x indicator that xi and yi differ, okay, for all vectors x and y in the Cartesian product xn. Okay, so this property, let's call this property for future use as property star. So note that if ci of x, if the ith coefficient as a function of the entire vector x does not depend on x, but it is just some constant ci, then this is exactly the bounded differences property satisfied with the vector c1 up to cn. But however, we are being more flexible in that the coefficient, the sensitivity at the ith coordinate, if there is a difference, depends on ci of x, and that ci can depend on x. Okay, so this is strictly more general than the standard bounded differences property, and we'll also assume that z is the result of applying f to x to the vector x. So x is really x1 through n. We're omitting the subscript where the xi are all independent. Okay, so this is the setting, and we'll actually show that the transportation method actually kicks in very neatly to help us bound the tails of Z. So before that, let us recall that we have actually considered concentration of such functions beyond bounded differences in our application of the entropy method that we saw before the transportation method. So let's recall that before we move on. Recall a typical, let's say, beyond bounded differences result. Result that we derived using the entropy method. okay, earlier. So in fact, the results from the entropy method do help us analyze this situation above. So if z equal to f of x and zi is defined as the minimum over the ith coordinate of f when you fix all the other components to be the components of x. So this is zi, this is really zi as a function of x, okay, in fact, yeah. So xi minus 1, xi prime, and xi plus 1 going all the way up to n for all I. And if we have that the summation of I equal to 1 to n, the difference between z and zi square is bounded above by an absolute constant v, say almost surely, then the entropy method helped us establish an upper tail inequality, saying that for all t positive, the probability under the natural measure of x1 through xn of z exceeding its own expectation plus t is at most, let's say, e raised to minus t square by 2b. So we got a sub-Gaussian tail bound with the sub-Gaussianity constant depending on this upper bound on the almost sure upper bound on summation z minus zi whole square. Okay, so this was basically the way we did it. One of the key ingredients in this proof using the entropy method was to first show a modified log Sobolev inequality, if you recall. Okay, and that helped us basically apply the entropy method to derive such a result. So how can we map this to the problem setting at hand? So if you recall, so we need to satisfy this condition here. Okay, and if we have the condition star for our function f, you can easily argue that an upper bound v for z minus zi whole square is can be used with summation ci x the whole square maximum over all possible vectors x. Okay, pardon me. So this is basically because if you have condition star, then the least that f of y can get. Okay, so if you just think of holding x constant at all positions but position I, and minimizing and trying to find the least value of y, where y is defined as x in all but the ith coordinate, and letting it range freely over the ith coordinate, then on the right hand side you basically have only one term, which is the indicator xi not equal to yi, and for that term an almost sure upper bound is ci of x. Okay, so by analogy you can just sum over all n coordinates of the squares of the differences to get v as to get summation ci square x as a proxy for v. So let me just remark here that the condition star that we have yields v equal to the supremum over all pairs x of the sum I equal to 1 to n ci square of x. Okay, so you can apply the entropy method to derive this inequality, with v being exactly this quantity here, the maximum over all x of ci square x. Now there are several unanswered questions. Among them is the issue of what about the tail bound for the other side. So this is only a right side tail bound. What about the left tail and so on? So in fact what we will show now using the transportation method are two things. So we will show using the transportation method two things. One is we will recover the same upper tail bound here using ideas purely from transportation, optimal transportation. So the same upper tail bound for Z as above, and moreover we will rather remarkably show without any extra effort a lower tail bound as well. So a lower tail bound, that is the probability that Z is less than equal to Ez minus t, with much better variance parameter, in fact with variance parameter of only the expectation of the sum of Ci square x. Okay, not even the supremum value of Ci square x over all x, supremum of summation Ci square x, but in fact a potentially much smaller parameter, which is only the average value of summation Ci square x, okay, without any extra effort. Okay, so this is what the transportation method allows us to show. As a side note, if you were wondering what about the scope of the entropy method to prove a lower tail bound, in fact there is no such lower tail bound known using ideas from the entropy method without additional assumptions. So the lower tail bound not currently known to be derivable using the entropy method alone. Without perhaps additional assumptions that have to be made. So one example of an assumption that gives you a lower tail bound via the entropy method, which is there in the textbook, the concentration inequality textbook, is of the following form: that if you consider maximizing f at the ith location when all else is fixed, xi plus 1 to n, okay, and take the difference of this with the original f of x, then for instance this must be bounded by 1 almost sure. So such an assumption helps you prove lower tail bounds, but even then the lower tail bound does not have this improved variance parameter. You can look this lower tail bound derivation up in the textbook using the entropy method. But what is rather remarkable here, is that the transportation method easily allows us to prove these two results with essentially the same amount of effort. Okay, so let's go ahead and write down the formal result, which we will argue in this and the next lecture using the transportation method. So this is the following result. So let's assume x is a vector of independent random variables distributed according to the probability distribution P, which is a product measure over n coordinates, and let's set z equal to f of x, and we have f satisfying the property that you can bound f of x minus you can bound f of y minus f of x f of x minus f of y in terms of x dependent Hamming sensitivities. And let us also denote v as the expected value under the natural distribution of x of summation ci square of x, and v infinity as the largest value of such a sum of squared coefficients. So sup over all possible arguments x of I equal to 1 summation I equal to n ci square of x. So v infinity is clearly lower bounded by v, and the result of the theorem is that under the P measure, the measure of the independent xi's, the probability is that z exceeds EPZ plus T is at most e raised to minus T square by 2 V infinity, and on the lower tail side, on the left tail side, probability is that z less than expected value of z minus T is at most e raised to minus T square by 2 V, which is a much lesser sub-Gaussianity constant than V infinity in many cases, and this holds for all T positive. So this is the content of this beyond bounded differences kind of result, for which the transportation method comes in very handy, as we will see. So let's move on to the proof of this result, which will take us some time to execute. But at a high level, I'll outline in this lecture the high level idea of the proof. So we're going to use the transportation lemma. So the first order of business is to consider a probability measure Q absolutely continuous with respect to P, and let x comma y distributed according to P be a coupling of the measures P and Q. Okay, in that order. So x is distributed, the marginal x follows the distribution P, the marginal y is distributed according to Q, and P is a product measure. Okay, so P is really P1 all the way up to Pn, which we will also abbreviate as P1 to n or Pn occasionally. So let's consider bounding the expected value of z with respect to Q minus the expected value of z with respect to P as the transportation lemma requires. So by coupling, this is just equal to E under the coupling measure, the joint distribution P of Fy minus Fx. Okay. Now once we have Fy minus Fx together, we can invoke the beyond bounded differences kind of property, or the smoothness property for x in terms of the Hamming distance, to say that this is upper bounded by the sum of Ci of y into indicator yi not equal to xi. So this is by the F smoothness property, which is also the equation star that we wrote earlier. Now what we can do is we can condition this expectation iteratively on y itself, the entire vector y. So imagine taking a double expectation with respect to y, and so if you do that, you basically get the expected value of some I equal to 1 to n Ci of y into the expected value of the indicator given y. That's just the probability of yi not equal to xi given the vector y. So this is just by the property of iterated expectation. Okay. And now what we can do is the thing inside the expectation looks like an inner product. It's the summation of I equal to 1 to n into some ai into some bi. So to upper bound it, we can use something like Cauchy-Schwarz, whereby we get I equal to 1 to n Ci y square under the square root into another summation of all these probabilities yi not equal to xi given y the whole square under the square root. Okay, so this is basically by Cauchy-Schwarz. And which is inside the expectation. Nothing about the expectation is being used here. At this point, to continue upper bounding this, we can now use the probability version of Cauchy-Schwarz, Which basically says that the expected value of a product of random variables. So there are two random variables sitting here. This is the first random variable and this is the second random variable. The product of two random variables, the expected value of two random variables is at most the L2 norm in some sense of these, the product of the L2 norms of these random variables, where L2 norm is defined with respect to the expectation operator. So formally this just becomes the expected value of some Ci y square under the square root into another square root of the expected value of the sum of all these probabilities, conditional probabilities square. Okay, this is again by Cauchy-Schwarz in its probabilistic flavor. Okay, and it's useful to notice here that the quantity inside the first expectation by definition is almost surely upper bounded by V infinity. Okay, as per our definition of V infinity is basically the largest possible value of the sum of Ci squares. Okay, so finally we get that EQZ minus EPZ is upper bounded by square root V infinity into the square root of this sort of transportation cost like term. Okay, so we get this. Now along very similar lines, we can apply the same technique to the random variable minus f of x or minus z, okay, to get the following. So EQ minus z minus EP minus z can in a very similar fashion be upper bounded. So what you will have now is basically you will have the expected value of Ci summation Ci x square. So expected value so we'll have x instead of y. Okay, we'll have x playing the role of y into the same square root of the expected value of the sum of these conditional probabilities given x instead of given y. Okay, and by definition this is exactly equal to V because now the expectation is over the x or the p measure. Okay, so notice that we have basically obtained two bounds, one for the difference of expectations of z and one for the difference of expectations of minus z. In both cases there is a constant that shows up which is either V infinity or V. So the z inequality will help us give a right tail bound for z and the minus z inequality will help us give a left tail bound concentration bound for z. And all we need to handle is that we need to show that the second term, which is this transportation like cost, which is the expected value of sum of conditional probabilities of discrepancy square, should somehow be related or upper bounded by the divergence between the measures. Okay, so therefore the upshot of this calculation is that via the transportation lemma, we will be done if we can show okay what is called Marton's conditional transportation cost inequality. which is essentially the statement that there exists a coupling of x and y, or of the measures p and q, such that under that coupling the expected value of the conditional probability of discrepancy, the square of it, given x plus the same symmetric version given y. Okay, so the sum of these two conditional discrepancy probability squares is at most 2 dqp for all probability measures q absolutely continuous with respect to p, which is basically assumed to be a product measure. Okay, so this is exactly Merton's conditional transportation cost inequality, which we will show in the next lecture. But assuming this, what one can do is one can just go and use it in the appropriate tail bounds to bound these conditional probabilities. We are bounding the sum of these conditional probabilities, probability squares. So that naturally implies the same bound for each of these conditional probability squares, and you can relate it to the divergence and then use the transportation lemma to sort of transfer it to the control of the log moment generating function, and finally Chernoff will kick in to give you the appropriate tail bound. Okay, so that basically is the summary of how the transportation method gives you both tail bounds with the appropriate variance parameters v infinity or v, just by invoking this powerful Merton's conditional transportation cost inequality, which will be the subject of the next lecture. Thank you.